Are you having a little trouble with Chapter 6 OWL? I'm making this video to help you out just in case you need a little bit of extra assistance. If you're looking at a problem like we see in number 2, where you have a reaction and they give you a delta H value, notice in this case that the delta H is negative, and so that's really important for you to understand that this reaction is going to be an exothermic reaction. So the question says, how many grams of H2O2 liquid would have to react to produce at least 35.1 kilojoules of energy? If this reaction goes through its process just one time, it's going to release this amount of energy, negative 196. So this is just really like a mole train problem. You start off with your 35.1 kilojoules of energy. And you're going to use your information up there in the equation, or as part of the equation. This should really say per mole of reaction. So for every one time that reaction runs, you're going to get a negative 196 kilojoules of energy out of it. So let's put a negative 196 down here on the bottom so our units will cancel. And because it says to produce 35.1 kilojoules of energy, that would assume that that's also a negative. So your negatives are going to cancel out and you won't have a negative amount of grams, which would be impossible, okay? And so this is going to be in kilojoules, and that's per mole of reaction. So 1 mole will go on top. And then you have to think about how many moles of H2O2 do I have in the reaction? That's got a 2 beside it. So if you wanted to, you could skip this step and just say, well, for every 2 moles of H2O2, I'm going to get out 196 kilojoules of energy, okay? And this is H2O2, and then we would need to look up the molar mass of H2O2 in order to figure out grams. So for every 1 mole of H2O2, look up on the periodic table to see how much that's going to weigh. And hydrogen weighs about 1.01, oxygen weighs 16, so 16 and 16 would be 32. 32 plus 2.02 would end up giving you 34.02. And so then when we do our math, let's plug that in real quick, and this is grams. Okay, so 35.1 times 2 times 34.02 divided by 196. Our negatives cancel out, and I got 12.18 grams. But we're going to try this as 12.2 grams on that one. And that is correct. You notice they did the same situation that I did through that one. So that's how you do a problem that already has a delta H given to you. Let's look at another type of problem here. Okay, so in a specific heat problem, you're going to be using Q is equal to MCAT. In this one, in the laboratory, a student finds that it takes a certain amount of joules of heat energy. So we have this many joules of energy. That would be our Q. To increase the temperature of 13 grams of gaseous helium from 21.6 to 39.1 degrees Celsius. And then they want you to calculate the specific heat from the data. So Q equals MCAT. You're looking for C, which is the specific heat, and you've got all the other information, and it's just a plug and chug type problem. So whenever I'm going to take this out of scientific notation, so that's going to be 1,000, 0, 90 for the Q. The mass is 13. C, we don't know. And our change in temperature is, we have final minus initial. So we've got, this is our final. Here's our initial. 39.1 minus 21.6, which gives us 17.5. So I'm going to go ahead and plug in 17.5 here. And then we're just going to isolate C. Okay, so we'll take these 1090 divided by 13 times 17.5. Make sure when you're doing this in your calculator, this is a common mistake, and hopefully you've gotten past this, but use parentheses if you're going to multiply those numbers in the denominator. Okay. So we've got 1090 divided by 13 and also divided by 17.5, and I got 14.79 for the answer. So let's check that real quickly. Sorry, I didn't get 14.79. I got 4.79. All right. And that is correct. So we see all of the information there, and this was just a plug and chug. Notice that they're using S for C. So S is specific heat. It's also given as the value of C. And we didn't have to calculate the experimental error, but that's what you're doing whenever you're working with just Q equals MCAT. Let's look at another type question that you are maybe having problems with. Okay, so in this question, it says how much heat energy is required to raise the temperature of 14.1 grams of gaseous helium from 20.3 to 36.6 degrees Celsius. It's the same type of question. It's a Q equals MCAT question, except they don't give us the Q part, and it doesn't seem like we have enough information to answer that question. So Q equals MC delta T. We are looking for, in this case, Q. We have the mass. We can plug that in. Just plug it in, plug it in. We have the temperature. So the final temperature is here. The initial temperature is here. Subtract 36.6 minus 20.3 and plug that in there. And then it's like, well, what about C? Look at your little reference table right here. See where it says references, and it actually says use the references to access important values if needed for this question. So if we click on this reference table, then it says periodic table, general chemistry table, organic chemistry tables, and significant figures. How about general chemistry tables? And that opens up a new tab for us. And over here we have some constants. Later you'll learn about acids and bases, electrochemistry, and then right down here we have specific heats under thermodynamics. So that's what we need. And we need helium. So we look up helium and notice it is 5.19. And so that's what we're going to end up plugging in for our C value. Take all those numbers, multiply them together, and I got to look at my numbers again to see what we get, but that's how you're going to work that type of problem, okay? And you'll end up with the answer that you need for that one. So you've got those reference tables right there. Let's look at another type of problem that you are encountering. Get this off the screen. Okay, a sample of gaseous helium is heated with an electrical coil. If you've got this amount of joules added to this initially, what's the final temperature? That's the same kind of problem that you just saw, except this time you're using a different part of Q equals MCAT. So you're still going to be using Q equals MC delta T, but you're looking for a portion of delta T. You're looking for the final temperature. Just remember that change in temperature is equal to TF minus TI. Okay. So again, it's just a plug it in, plug it in. This is your joules. This is your Q. This is your amount of energy. I'm sorry, your grams that you'll plug in here. You'll look up the specific heat for helium, just like we just did. And then you're going to solve for delta T, and then you can plug back into this. Okay? That's how you're going to look at that type of problem. Let's look at a different problem. See how you might work a coffee cup calorimeter problem. Okay, now this particular type problem, this is where you have one substance, you know the specific heat of, say, water, you drop a substance into water, and then you're calculating the specific heat of that substance. Here's a concept that you must get into your head. Heat gained is equal to heat lost. The way we will do that, I'm going to do heat positive equals heat lost. So that would be heat negative. So you could say Q equals negative Q. And then what does Q actually equal? MCAT. So MC delta T equals negative MC delta T. Okay, so take your information that you're given for each substance. You got to think about which one's losing heat, which one's gaining heat. So she heats the nickel to this temperature and then drops it into a cup of water, and the water is at this temperature. The final temperature is the final temperature of both the nickel and the water. So this is your TF for both of the substances. Okay, so which one is losing heat energy? That's right, the nickel. So the nickel's going to be, all the nickel information is going to be on this side of the equation. And then this side is going to be the water information. Okay, and we're looking for C for the nickel. That's what we're looking for. Now, granted, you could just look it up, but it may not be the same answer. This is an experimental result, so it may not be the same answer that you find on your reference table. Do you try to just cheat it and not do the math? Okay, so we can plug in the 19.4 grams right here into our mass for the nickel. Whoops, that's supposed to be a 4. Anyway, I think you get the idea of what you're supposed to do with this. I may not be able to completely work it out there for you, but 19.4 would go here. We're looking for C. We don't know. I'm just going to put C over here at the end. That's going to be our unknown variable. And change in temperature, it's final minus initial. So the final temperature of the nickel is 26.04. The initial temperature of the nickel is 99.39. So you're going to end up with a negative value right here. Well, watch this. You also have a negative value here. So whenever you have a negative times a negative, your specific heat will not be negative. It'll end up being positive. Okay, and then use the information for water. Plug in the mass of water here, the specific heat of water. If you don't remember the specific heat of water, look it up, but it is something that'll start sticking into your head the more that you use it. 4.184 joules per gram times degrees Celsius, and then plug in your delta T for your water. So remember, final, here's the final for water and nickel minus initial. And you just plug that information in and solve for C. Okay, let's look at another type of problem that you're encountering, a Hess's Law type problem. In a Hess's Law problem, we've got a situation that looks like this. They have the standard enthalpy change for this reaction is 712 kilojoules at 298. So they gave you a delta H. That really should say kilojoules per mole of reaction. Okay, they're kind of, it's not giving you all the information that it needs to give you there to help you think about solving that problem. So per mole of reaction would have been nice to see. Okay, and then it says, what is the standard enthalpy change for this reaction? So let's see what is similar about the two reactions. Well, it looks like that the first reaction is breaking down, a decomposition, and the second reaction is a synthesis reaction. So maybe from your reading and maybe from doing that FET the other day with Mr. Winston, you might have gotten the idea that if you flip a reaction or reverse a reaction, then the sign of delta H would reverse. And so that's actually what happens here. I'm going to go ahead and plug an answer into this one. And so this should be, since all we did with this one is just flip the reaction, it should be negative 712 kilojoules per mole. And so that's it. That's a correct answer on that one. Okay, let's look at Hess's law with two reactions. So whenever you have two reactions and you end up with an overall reaction, all you have to do is add your reactions together to get that overall reaction. But whatever you do to one of the reactions, you have to do to delta H. So, like, for instance, if you have to flip a reaction, you would change the sign. If you multiply the reaction, say, by some variable, then you would multiply delta H by that same variable. Okay, so let's see what we would need to do to get this reaction. We've got NiO as a solid here, and I see NiO right there. But notice that NiO in the top reaction has a 2 in front of it. So I would need to divide this entire reaction by 2 in order to get rid of that NiO. And also I noticed something else about it. Notice that NiO is on the right-hand side, and it is not in the bottom reaction. So this number 1 needs to be flipped, which is going to change the sign to positive, and it needs to be divided by 2 in order to get nickel oxide on the proper side. Okay, now that'll give us nickel oxide, that'll give us nickel where it needs to be, it gets rid of the 2's. And then look at the other part of this. We have mercury, Hg. And mercury happens to be on the correct side of the equation. They're both on the left, but mercury in number 2 in that reaction is multiplied by 2. So we would need to divide this equation by 2, which means we need to divide delta H by 2 as well. Okay, so now how do we get the delta H for this overall reaction? Well, all we have to do is add them up and take care of what we manipulated. We changed that negative 479 to a positive, so we would have to take 479.4 divided by 2 plus a negative 181.6 also divided by 2. And when I tally that up, I gotta punch it in my calculator, right? I get a 148.9 as the overall delta H for that reaction after I add those up. Okay, so I'm going to punch this in, and that was 148.9. Now let's just go back and see what we did. I took this divided by 2, it was positive divided by 2, and then I added it to the negative 181.6, but I divided negative 181.6 by 2 before I added it, okay? So you might want to check that to see if you see how I got my answer there. All right, so I'm going to submit this, and that is correct. All right. Notice they did the same kind of situation here. Gives you all the stuff I just said in writing. Okay, let's look at number 10 and see what they're asking you to do. Using standard heats of formation, calculate the enthalpy change for the following reaction. Now, we had not yet gotten to one of these in class, but hopefully you read about it, and it's also in your lecture guide of how you would do an equation like this. Basically, all you have to do is take all of the information, the standard enthalpies of reaction for the products, and subtract them from the standard enthalpies of reaction of reactants. Okay, you do have to multiply them by their coefficients, but it's P minus R equals delta H. Okay, so let's find those numbers. Well, for any element that it's in its standard state, the delta H will be 0, but let's go ahead and check it out. Where are you going to get that? Well, if you have a book, that's great. Or you go to your reference table here and pull up. You want thermodynamic data. You want delta H. Now, we were looking for sulfur and carbon, so I want to show you those two real quick. Carbon in the graphite form, notice it's delta H is 0 because that is the standard state for carbon. Let's check out sulfur real quickly. I'm pretty sure that's the standard state for sulfur, but I could be wrong. It's been a little while. Now, sulfur rhombic is 0. Sulfur solid monoclinic is 0.3. Sulfur as a gas is 278. So I believe that one said that was rhombic. So let's check it out. It said rhombic, so that's a 0. And carbon is a 0. So we only need SO2 and we need carbon monoxide. Carbon monoxide as a gas, SO2 also as a gas. Okay, so since I'm in the sulfurs, SO2 as a gas is a negative 296.8. See it right here. And then I'm going to go up to carbon dioxide. Carbon monoxide, sorry. Carbon monoxide is a negative 110.5. Okay, and now let's look and see how we need to plug those in. Okay, so sulfur dioxide is a product, so I'm going to take negative 296. Let me just write this in because I said it was products minus reactants. So negative 296.8, which was its number, minus the carbon monoxide's number, but there's a 2 in front of it, so you have to multiply that times 2. So minus 2 times negative 110.5. These aren't really hard problems to do. Just keep up with your numbers and your signs. That's the biggest thing, okay? It's a little meticulous to make sure you have the signs right, but I'm going to plug this in my calculator just how I have it written. Negative 296.8 minus 2 times negative 110.5. And I get a negative 75.8. So let's try that answer out real quickly. Negative 75.8. And that is correct. Notice they did everything that I did. Actually, they put the zeros in, but if you have a 0 for those products, then you don't have to put those in. All right, we have one more type of reaction. So let's look at number 11 and see how you would work a problem like that. So number 11, a scientist measured the standard enthalpy change for the following reaction to be negative 771.8 kilojoules. Based on this value and the standard enthalpies of formation for the other substances, the standard enthalpy for formation for water is what? So you don't know water. You're going to be looking for this. We're going to make this an X. And since there's a 2 in front of water, we're going to make this a 2X. Okay? So we don't know that value. Now, here's one thing you need to keep straight. It's products minus reactants. Okay, so P minus R is going to equal, they gave us what the delta H for this reaction is, negative 771.8. Okay, so we know that delta H. What we don't know is what the standard enthalpy change for liquid water is, and our job is to find that. So we're going to be looking for 2X. Okay, so I'm going to go ahead and plug that in on this side of the equation. And then I'm supposed to add that to nitrogen, but now nitrogen's in its standard state. It's a gas, so that number would be 0. I'm not even going to put that into my equation. And then hydrogen is also a gas in its standard state, so that number would be a 0 when I look it up. So the only number I need to look up here is nitrogen monoxide, but I'm going to go ahead and set this up. 2x minus 2 times whatever nitrogen monoxide's value is. So I'm going to leave a parentheses for that, is equal to negative 771.8. Okay, so I'm going to come back over here and I'm going to look at what NO's value is on my thermo table. So let's see, NO, nitrogen, 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 nickel, nitrogen. Okay, so NO as a gas is 90.3. Okay, let's go back. So then I'll plug in 90.3 right here. And why do I have a 2 in front of that? Remember, nitrogen monoxide had a 2 right here. So there are 2 nitrogen monoxides. You have to plug that in. So now you're just simply going to solve for X. That's all you have to do here. So 2 times 90.3. I'm going to simplify that a little bit. I've got a 180.6. So 2x minus 180.6 equals 771.8. Wish I could write faster. And then I'm going to add this to both sides, plus 180.6. Whoops, I forgot that negative sign. See, it's easy to do. Plus 180.6. And then I'll have 2x is equal to whatever that is, and then I'll divide by 2, and it looks like that's going to be a negative value, right? So I've got negative 771.8 plus 180.6, and that's negative 592. I need to divide that by 2, and that means x is a negative 295.6. So we're going to try this number out here. Negative 295.6. See if I got it right. Okay. Submit. And that is correct. Okay. So it's really not hard to do those types of problems. It's just products minus reactants. I hope that helps you. I've changed the submission date for some of you that were struggling on this until Wednesday. I will not change it again. So take care of your business. You're going to also be working on Chapter 17 as well this week. So get that taken care of, get started on it, and I will see you in class tomorrow.